Thank you again, Professor Tia, and for your kind introduction, and also thank you to the organizer, the Carbon Research Editorial Office, for having me today to talk about my research. And here today, I will focus on the carbon-based additives in organic coatings for the corrosion protection of mild steel. There are 4 parts to my talk today. So I'll talk about the introduction to corrosion protection of mild steel, the fundamentals, why coatings matter, and what we mean by sustainable materials and sustainable additives. I'll give a bit of background on research that's been carried out for carbon additives in organic coatings, primarily like graphene oxide, nanocellulose, and biochar. Then I'll deep dive into one of my publications on how we actually do the corrosion protection characterization using electrochemical techniques and other characterizations, and also from my experience of doing some innovation-related management at university, and how we can use patterns to kind of guide us in future directions for this kind of research. So corrosion is a huge problem, and the size of this industry, the cost to the industry is about $2.5 trillion, and this is estimated by the Association for Materials Protection Performance, used to be known as the National Association for Corrosion Engineers, for those who have been following this company for a while. So this is a huge number. It's about 2.4% of the annual global GDP. It's actually the size as well of all military expenditure in the world, including it's also the size of the annual spending people have on cars, and not very much bigger than the size of Canada's economy. So you're looking at a huge number here. And so protective coatings, they are very valuable because they help to mitigate corrosions. And normally when we use these coatings, we want them to be cost-effective, easy to apply, and can operate in various environmental conditions. So you're talking about having good mechanical strength and also good adhesion properties to the material you want to protect. And very often we actually use nowadays organic coatings. I'll give you some examples a bit later. And well, we care a lot in my research here. I focus primarily on the mild steel substrate. It's very, very important because it's like it's a workhorse in industrial settings. It's used in almost all types of industrial infrastructure. So mild steel is also known as low carbon steel. It has normally there's some elements of carbon inside, about 0.05% to 0.25%. It's primarily made from iron, and we use it a lot because it's strong, it's cost effective, it's easy to machine, and also to weld. It's got many other favorable properties. It's used in construction, making cars, furniture, machinery, pipelines, and you get them in also different grades. And normally the different grade comes with different carbon content inside, but we don't focus so much on the carbon in the mild steel. We'll talk more about the carbon additives we add to coatings to protect the mild steel. But just so you know, so normally the mild steel that we use in the real life is not really in this form that we see on the left hand side here. It's not normally what we have to do is we process the iron ore, and then it goes through a lot of very energy intensive processes before it comes out. When it's actually after manufacturing, the mild steel is normally unstable, and because it's basically chemically unstable because it's not at the thermodynamic equilibrium. So if it's not protected, such as when you use them in maritime environments, which has like high concentration of corrosive species like chloride ions, this mild steel can actually react and degrade, and then it's not very favorable. And the most famous type of degradation you see on the right is actually rusting, and it's actually the formation of iron oxide particles. And other types of steel you might come across, like stainless steel or galvanized steel, they are also kind of like, they're more expensive than they are normally protected steel that is protected in different ways. Yeah. But I'll go back to mild steel. But before we go into the details, I will just focus on some of the fundamentals of corrosion. And corrosion is actually just an electrochemical process. You have the anodic side, you have the cathodic side, you have the electron path. Let me see if I can you can see, okay, you got the electron path and all the four components must be present for actually corrosion to occur. Here, we can start with, like, at the anodic side, what normally happens is that the metal can lose electrons and then it's oxidized. And these electrons that's lost actually travels inside the mild steel to a cathodic area. And the cathodic area, the electrons will react with the oxygen to produce water, and then the water will give some hydroxide ions, and the hydroxide ions will then travel in the electrolyte. In this case, it's water, but there can be other types of electrolytes as well. Not water, the electrolyte is water, so these hydroxide ions, they travel back to the anodic area and then oxidize the iron, and then you form these iron hydroxides. And these iron hydroxides, if they are not well contained, they can actually flake and then come off, and this actually leads to material loss. So when we want to talk about stopping corrosion, we want to actually disrupt this electrochemical process. One of the ways you can do that, you can, for instance, try and maintain the same potential on the mild steel using impressed current, or other ways we can do, and I'll go into some details later. You can introduce some sacrificial material that's more electroactive to react. Yeah. Okay. So the main strategies we normally deploy, there are three types. You can have a passivation method. You can have the coatings, or you can also introduce inhibitors. So in the passivation, this one is what you see maybe in galvanized steel and stainless steel. Is you maybe you try to basically, in galvanized steel you add a passive layer. In stainless steel you normally add chromium. So then they will form these chromates that actually passivate the surface. But some of these techniques generally can be more expensive. The cheaper one, cheaper for mild steel, is you can use coatings, which is, you apply some organic or composite films that ideally what you want is to physically block the corrosive species. So corrosive species in maritime environment will be like chloride ions. In some acidic environments, it will be the sulfuric ions and so forth. And also, if you can also try and block oxygen and water in, say, humid places, but that, of course, is not very straightforward. I would come to discuss a bit about that later as well. And then the last and not least common method is also using inhibitors. So this one, you try to add soluble species to the corrosion medium that hopefully will help to block the anodic and cathodic sides. And I also mentioned earlier, you can also introduce a current to maintain a surface potential that's almost the same. So you don't actually have cathodic anodic areas that might trigger the electrochemical process. So when we talk about sustainable materials, so this one of the framework that I kind of developed over the years, like what do we actually mean by this? It can be defined based on choice of feedstock or the processing technique that you deploy. So when you talk about feedstock, more specifically, you want feedstock to be renewable. Meaning it can be replenished. It's not something you mine from the ground and so forth. And here renewability is relevant because first you want to make sure that you can always have replenishable material, and one of this is example is biomass, because it can be synthesized from photosynthesis. And also biomass is nice because you can kind of say like it's carbon neutral, because then you don't actually you're not actually extracting it from the ground. Waste also can be considered as a renewable feedstock, and this is tying into this idea of like circular economy. For green processing techniques, you can have, most important for them is that they can be easily electrified. And here we have, we can talk about hydrothermal processes. We can also have advanced mechanochemical techniques. And here we refer to, basically just bore milling. And microwave pyrolysis is something new that I just recently came across from engaging in this carbon research committee. Not something I use, but it's also one potential method that you can claim is green processing, because it can be powered using electricity. We have two parts to what you mean by sustainable materials. One is the feedstock that you use to make the material. The other part is the processing technique that you need. Yeah. Okay. So a bit of background. of carbon-based additives and coatings. So just so that you know that this is not exactly very new, but it's also not exactly very old as well. So, but before I talk about the carbon-based additives, I'll describe the organic coatings that we have that normally you see published in literature. There are three types. Actually, there are more than three types, but these are the three most commonly seen ones in academic literature. You have epoxy, and this is the one I work with most of the all the time actually, because it's cheap, it's durable, it has very good adhesion properties to mouthfeel, and in some cases you also, not in some cases, but majority of the case, you often see that this zinc is actually added into this epoxy coating, and the reason is because zinc here gives the provides galvanic and some kind of barrier protection. And galvanic protection here means that you have actually the zinc, which is more electroactive than mouthsteel. So in the presence of corrosive species, the zinc will be oxidized first, and so it's kind of like sacrificed. And hence, we sometimes call the zinc in this configuration the sacrificial anode. So the excess electrons from the zinc reaction then protect the mouthfeel, which is the cathode in this case. And then this kind of mechanism is one type of protection we call cathodic protection, also known as galvanic protection. So normally with the zinc at the initial stages, you try to enable a flow of current, and then the zinc will then react with the corrosive species to form corrosion products. And normally when you use zinc-rich coatings, you want to have heavy loading of the zinc, usually about 90% weight percentage is encouraged. And but when you do this, normally what will happen is that you might reduce the mechanical properties, and you can lead to coatings that are quite porous, because now you don't have a lot of epoxy. So then you might also have issues with adhesion, and hence additives can be added as well to supplement the performance of zinc-rich coatings. We hope that then this kind of like fillers, they have good conductivity and also good mechanical strength. So that's epoxy. The other problem with epoxy we normally see is that it degrades in UV, under UV, so not very good for performance under the sunlight. So one of my research is to actually see if we can improve UV performance of epoxy coatings. The other two, I haven't started looking into them, but you do see them published in literature, polyurethane and polyaniline as well. What we know about polyurethane, it's got better one of the things is got better UV performance than epoxy. So you do see them being deployed in commercial coatings outdoors, but it's actually prone to fungal activity in humid environments. And polyaniline, we don't study it so much, but it can be blended with epoxy, and but it's been shown to have poor mechanical properties, and also doesn't stick to mouthfeel very well. So hence, we mostly work with I mostly work with epoxy. So there actually in the past, with people have added a lot of types of additives, but most of the additives in the past are normally metal-based. You see silicon oxide, aluminum oxide, chromates, even iron oxide as well, zinc oxide, titanium dioxide. So they are added to improve barrier protection, corrosion resistance, UV protection, and mechanical strength. Clay also is added. Clay is a kind of magnesium aluminum silicate that sometimes people add. But for my research, I'm more interested actually in carbon-based additives, because why? They can be deemed to be sustainable, mainly because this kind of additives, you can derive them from renewable biomass. And on top of that, most of the techniques so there are new techniques now we can use to make these carbon-based additives that can be considered green. So like hydrothermal processes, or using advanced the ball milling, and also micropyrolysis. So actually what we are trying to promote here is that we want to say that carbon-based additives can offer a path to high performance coatings, and with a lower environmental footprint. Yeah, so one of the first actually early reports of carbon-based additives in coatings is actually use of graphene. And for graphene, it's not surprising, because soon after the discovery of graphene as a two-dimensional material, it led to the Nobel Prize of Geim and Novoselov. They become this graphene and related graphene oxide suddenly exploded, used in almost every application areas. And corrosion protection is also definitely one of the areas that that was looked into. And the early efforts using graphene directly on mouthsteel involved the seeding or growth of graphene on exposed metal surfaces. So they weren't really used as coatings. They were just people try to deposit deposit some seed and then see if the graphene or graphene oxide flakes can actually grow. And they're hoping that if it grows, it can actually confer some kind of corrosion protection to the mouthsteel surface. But soon after that, efforts to integrate graphene or graphene oxide into organic coatings, such as epoxy, they started, and we first see them reported in actually 2015. And when these early efforts were reported, they normally come in, they try to functionalize the graphene. And the reason for that is because they want to ensure that there's good dispersibility and also adhesion of the graphene to the inside the coating or to the mouthsteel. So this is on the left. They developed this titanium oxide graphene oxide hybrids, and then what they saw was that these additives improve the mechanical performance as well as improve the corrosion resistance. Then later on, not long after that, we start seeing publications related to graphene oxide as well in epoxy coatings. Again, they are functionalized to encourage covalent bonding to the epoxy resin and also to prevent agglomeration. And then around the same time as well, people try to come up with smart ways to develop graphene and epoxy coatings. And this one was done using waterborne epoxy resin. So this is in 2016. And ever since then, there's been quite a lot of research in this area. It's actually, for myself, I find it actually quite tricky if you want to do innovation in this space, it's actually quite saturated. But so this is one of the early carbon-based additives that were added to organic coatings for corrosion studies. Not long after that as well, we started seeing deployment of nanocellulose. So cellulose is one of the most abundant materials on this planet. We like it because it's renewable, biodegradable, and also biocompatible. And as you know, in this community, it's made up of cellulose, made up of repeating glucose units. They have this beta-1,4 glycosidic links between the first and the fourth carbon of each glucose. And when we talk about nanocellulose, we're talking about cellulose whose particle size normally tens of nanometers up to maybe 500 nanometers or half a micron. Then normally, again, we expect them to have, if you introduce them, they can give high mechanical strength. And there's also have a large surface area given because of their nano properties. So on the left was one of the first reported deployment of nanocellulose used in epoxy coating. So the nanocellulose was synthesized from microcrystalline cellulose using acid hydrolysis, sulfuric acid hydrolysis. Then later, in about around 2020, we started seeing more innovative deployment of nanocellulose epoxy coatings. And at least with a story, not just I synthesized for microcrystalline and I deposited in the book. So this one, published by researchers from Universiti Science Malaysia in collaboration with researchers from Universiti de Lorraine, France. They actually synthesized cellulose nanocrystals from oil palm fronds. Oil palm fronds are the leaves of the palm oil. And why this is a very nice piece of research, because palm oil is a huge industry in Malaysia. And actually with this huge agriculture industry, you do expect a lot of waste. And oil palm fronds is one of the waste that they produce from this industry. So what these researchers try to do is see if we can actually add value to this oil palm fronds. And maybe one way we add value is to see if we can synthesize nanocellulose from this biomass waste, and then incorporate this nanocellulose into epoxy. In this case, they focus on zinc-rich coatings to see if it can improve the corrosion performance of zinc-rich coatings. And actually, they did. and they link the performance to hydrophobicity of the cellulose nanocrystals that they produce. And here it's a nice review for those who would like to know a bit more about nanocellulose in anti-corrosion coating. So normally, so it's much more advanced now than what we know back in 2020. So normally there are two types of nanocellulose. You have this nanocrystalline cellulose, and also you have this cellulose nanofibrils. So these are like long filaments. They can range from nanometers to micrometers, but the diameter is still on the scale of nanometers. And then the one on the top is nanocrystalline cellulose. These are more like rods, usually 50 nanometers to 500 nanometers long. The diameter is also around that size, and they both normally have good crystallinity and good mechanical properties. So one thing I want to say on this slide, from this slide, is that you can have you can deploy the nanocellulose normally on three areas, mainly as reinforcement fillers to improve the hydrophobicity of the coatings, and also you can functionize the nanocellulose to actually improve their dispersibility. Because what you don't actually want is one of the issues actually, if you just use nanocellulose on its own without any functionalization, it can be the particles can have large surface area and large surface reactivities. And what actually happens is when you take them out, say from the solvent that you keep them in, if you dry them out, they can actually start agglomerating. And so if you don't actually do some functionalization, and this is what often seen in many of these early reports, is that they start agglomerating and then they're not very well dispersed inside the coating. And when they're not very well dispersed, that actually limits the potential of that actually limits the performance of this nanocellulose in the coatings. More recently as well, quite a bit of developments is we begin to see the use of biochar reported inside organic coatings. And here is example one of the first I've seen on the use of biochar in zinc-rich epoxy coatings for the performance for conferring corrosion protection on mouse steel. And this is done by researchers, collaboration from researchers from the Academy of Sciences, as well as one of the leading coating laboratories in the world, in Denmark, the Technical University of Denmark. So this course, they are like a center that specializes in coating studies. So what they've done here is the hypothesis here is you have zinc-rich coatings which already perform quite well, but are there ways you can even improve the performance of the utilization of zinc inside these coatings? And in the past, before using biochar, people have tried to do it with carbon nanotubes, carbon fiber, graphite, graphene, which I've already talked about, and also reduced graphene oxide. So here they look at two types of biochar, one obtained from the spruce wood and another one obtained from straw. And what they actually saw was that the one because of the processing technique and there are some differences as well in the feedstock composition, the straw char, this straw spruce one is actually more porous and has higher electrical conductivity. So when you're working with zinc-rich epoxy coatings, actually you do want to promote some degree of electrical coating, because what you actually want to do here is you want to promote the electrons to actually travel between the zinc, so that this way the utilization of the zinc actually this big circles are actually zinc particles. The small black ones are the biochar nanoparticles, and what you actually want is actually a lot of electrons to travel around the zinc, so that they will the zinc will be oxidized first before the mouse steel, and when it oxidizes, it forms this passive zinc oxide. So this is one of the quite a nice study of how biochar is used in the zinc epoxy coatings. And more recently, we also see now biochar being used in waterborne epoxy coatings. And waterborne coatings are also becoming popular today, as they actually emit less volatile organic compounds compared to the traditional solvent-based coatings. But there's problem with waterborne coatings. Normally, they have reduced mechanical strength. They, and also when they dry out, when the water evaporates, they actually introduce a lot of defects and pores inside the epoxy resin. So where biochar actually is quite useful is, again, it can confer some mechanical strength. It has the high surface area. It has got microporous structure. So then you can play around with ideas to use the biochar to capture the corrosive species due to the high ion adsorption properties of the biochar. So in this study, they were playing around with different feedstock as well. I won't go into the details, but they found out that the cornstalk biochar gave them the best results. And again, this is because of they argue in this article that is to do with the pore structure. It forms a lot of multiple pathways, which kind of like slow down the penetration of corrosive species from reaching the the surface of the metal surface. And on top of that, there's also this hydroxyl and carboxyl groups that actually help improve the adhesion of the coating to the metal substrate. Yeah. And other things as well, they played around in this study was sonication. They found out that if they sonicate at a higher temperature, that actually improved the dispersion of the biochar inside the organic matrix, and then this helps again to minimize agglomeration and promote the formation of a denser and more uniform coating structure. So that's roughly most of the background that I wanted to talk about. And so now we'll go into how we actually do characterization of corrosion protection, and we'll use one of my early publications, one of the more important publications, to demonstrate this point. So this is done by the work was actually done by Okata Hamuda. Not sure if it's here today, but he was an excellent student. And he helped actually pioneer many of the techniques that we have here now at UBD. So we can do coatings research at a very high standard now. So to give you a bit of background how I came up with the hypothesis for this study. So Brunei Darussalam, we are located near the sea. So of course, we are a maritime environment. So we noticed that a lot of our mild steel infrastructure, you do see corrosion happening. So we always had that question like, how can we address and mitigate this problem? So when we first started this research, we actually came across that publication I told you about on using the nanocellulose in the epoxy coating. So we are not new in that sense. Even though when we had this idea, but we haven't come across the article. So we have to find what's a novel hypothesis that we can test. So as I said before, rather than just working with nanocellulose, why not we think about functionalizing the nanocellulose, introduce some kind of new properties to and what we thought about is why not we introduce sulfate groups, negative sulfate groups to the nanocellulose. And so we didn't start from a biomass feedstock here, because when we did this, we wanted to have a more controlled study. So use microcrystalline cellulose you can buy from Sigma Aldrich. Then we conducted some acid hydrolysis. And we know, of course, when you do some acid hydrolysis, you don't just break the glycosidic bonds. You can also sometimes add on the first hydroxyl, you can already start introducing sulfate groups. And then we then go a bit more extreme. We have a sulfation method using hydrochloronic acid. And then this, we hope, will also replace more of the hydroxyl groups in the nanocellulose and introduce even more sulfate groups. The aim here is actually to make this nanocellulose negatively charged. And the idea is we want it so charged that we hope it can actually repel or form an electrostatic barrier with the chloride ions. Because in the maritime environment, normally we mimic it using 3.5% sodium chloride solution. So the corrosive species is actually, in addition to the water, is also the chloride ions. And I'll say a few words later about why we are okay with the water, but more importantly, we want the chloride ions to be blocked. And we then hypothesized that introducing more of these sulfate groups will make the coating more negative, and then that will help to repel the, yeah. Okay. Yes. So here we have the SEM images of our nanocellulose. So on the left is actually the normal nanocellulose, and then on this one on the right here is the sulfated one. And then we see that actually the sulfated one looks smaller, but also has more porous areas in it. And that's not surprising, because to make this sulfated nanocellulose, we actually put it through more acid, more hydrolysis than the nanocellulose. So even though they all start from the same feedstock, but this has an additional step, so we're not surprised that actually the particle becomes smaller and has more porous areas. And of course, here they look very big because when we did this SEM, the sample was dried. We had to dry the sample and all that, so they agglomerate. But if you look at the TM, you will see that the size of our SNCC is actually on the order of like 40 nanometers. And then we also confirmed this later using dynamic light scattering. Here again, we have the XRD. This one on the left is the XRD of our the microcrystalline cellulose, nanocellulose, and the sulfated nanocellulose, just to show that there's some crystalline structures in them. On the right here is actually the XRD of the coated sample. So once we have made the nanocellulose and the sulfated nanocellulose, we deposit them into the epoxy, and then at different percentages by weight. So if you see the number 10, it means 10%. If the number 20, 20%. And then the ones here at the bottom are the just normal nanocellulose, and the one on the top is the sulfated ones. Then what we also, this XRD was taken after 30 days of immersing the coated samples. So once we prepare the coating, we coat it on the mouse tube, and then we put it into a corrosion chamber containing sodium chloride for 30 days, and then we take it out and we do an XRD. And what we see is that the ones with the sulfated nanocellulose, you don't actually see any chloride peaks. So we are and we only see them at the low concentration of nanocellulose. So we're quite confident that actually our hypothesis was working. And then this one is just, this image here is just an FTIR of our sulfated nanocellulose and the others, just to show that actually the sulfation happened. Won't go into the details, but quite a bit to get through. Here we also did some BET studies and BJT studies. So BET studies for surface area and BJT for surface volume. What I want to say here is that our nanocellulose, sodium and the sulfated nanocellulose, they follow a type 3 isotherm with the nitrogen weakly adsorbed, and then from this analysis we have some ideas that we know that there are pores, very small pores in our micropores, mesopores present, and they can have different shapes like rigid and rod-like and so forth. We also did some study on the zeta potential, and we confirmed that actually the sulfated nanocellulose has more negative zeta potential, so indicating that our negative hypothesis was actually working. Now on the next slide, we'll see that we actually do the electrochemical characterization for our coatings. So we have these TEFL plots. You get them from this technical potential dynamic polarization, PDP, and then we also conducted electrochemical impedance spectroscopy. So from the PDP, you get TEFL plots. This one, this figure here, and you have the anodic part, the cathodic part, and where it dips is an estimate for the corrosion rate. So where the position of this type of process, you can give you an idea the performance. So normally, if you want to have good corrosion protection, you want to go to the right in the way that this is plotted. So the ones here, we see that the SNCC, the sulfated nanocellulose, did have the best performance. From the EIS, we actually normally get three types of plot. You get the body plot, which is the real part of the impedance. Then you have the phase, and then you also have the Nyquist, which is related to the imaginary part of the impedance. Now and what I want to say from this is, I'll come to the body plot a bit later, but at least with the Nyquist plot, we can fit something called the equivalent electronic circuit. Normally, with a barrier, you think of them like introducing a double layer capacitance. So with a double layer capacitor, so with a double layer capacitor, normally you have time constants associated with it, and the different time constants that you get from fitting the equivalent electron circuits to this Nyquist plot give you an idea also what how the diffusion pathways are taking place for the corrosion. So if you have one time constant, you know there's only one electrochemical diffusion taking place, and then but if you have two, you will see that there are actually multiple, at least two diffusion pathways for the electrochemical reaction, and that sometimes indicate actually two corrosion reactions happening. And when you normally work in maritime in sodium chloride solution, you can have two, because one is the electrochemical reaction of the hydroxide ions, and the other one is to do with the chloride ions. So if you see two, you know that actually there's chloride species penetrating your coating. And here I'm going. We also look at the body plot. The body plot is quite important because it tells you something about the delamination and the damage which can happen to the coating. So delamination and damage are the primary factors that contribute to coating failure when exposed to a corrosive solution. And so here our body plots are for the ones on the top is from the sulfated nanocellulose. The ones on the bottom is not sulfated, just the nanocellulose on its own. This is the body plots after 30 days. And you have normally a capacitive region indicated in pink, and then there's the resistive region. So at low frequencies, here you see that the resistive regions give a clue as to whether there's coating delamination, and the increase in the resistive region is also an indication of delamination, which we actually saw occur more in coatings that have the nanocellulose. With the sulfated ones, you don't see so much. And also, I want to make a comment about the capacitive region. So if you have more capacitive region, you also have increased ability to repel corrosive ions species in your coating. So here, this is actually the hypothesis in the end that we tested. So we saw that for our sulfated nanocellulose, we do have actually still corrosion happening. No, there's actually from the time constants, we did confirm that there was at least for these ones we still have corrosion happening, but we say that it's actually just the uniform corrosion that occur on the metal surface with the hydroxide ions. Now this one is actually this is actually okay, because as long as the coating is intact, the rust that forms cannot come off. You can actually still be it can still be deemed as the system is working. But when you just use nanocellulose on its own, we did see that chloride ions can still penetrate the coating, and chloride ions are very dangerous because they can actually cause something called pitting corrosion, which is actually the loss of material that goes deeper. Okay. Okay, I'll try and speed up quickly. The last part is just about this is just about UV protection. We showed. I'll skip this slide. So I'll just go through the last part very quickly. Patterns very important because they are key to actually disclosure of technical information. I did some for this talk. I did some quick search. I showed that you can see that I did it for graphene, nanocellulose, and biochar. So in graphene, one of the first ones actually was published back in 2016. Back then, many patents, there was a trend to actually file patents in USA, so you might file in China first, and then there's a facility you can use called PCT that allows you to file in many jurisdictions outside. But more recently, most of the patents related to carbon-based additives and organic coatings, they're now mostly filed in China. And actually, when I did this, so like this is a recent one from the researchers from the Suzhou Institute of Technology. Also, we see coatings, additives used very recent. This one's from University of Shaanxi, late November 2025 in waterborne coatings. Nanocellulose, you get less number of results, which is good. I think when you want to innovate, you want to work in a space where you don't actually have a lot of competition. So you want to have less results. This is an example of nanocellulose. This one's from Chinese Academy of Sciences, one of the first ones filed in 2018. One thing I want to say is, if you look at my screenshots, I showed this one on the right. So actually, this patent information, you can find it easily. You don't need to pay money. You can actually go to this. I like the one maintained by the European Patent Office. It's called SFastNet, SFastNet, and it's actually very fast. And on top of this particular platform does machine translation. As you are aware, many of the patents are filed in Chinese. Even though my name is Chinese, I don't actually read or write Chinese, but I have to rely on machine translation available on the patent databases. And the SFastNet has one of the fastest and accurate, So what we also see now is, going back to the point I want to say on this slide, is that nanocellulose also used in coating for packaging. And I've also seen nanocellulose used in coating for cars, again, for mitigating corrosion. And I think this is a lot of interest to the biochar community, as I did a search I try to use very little keywords, but try and capture as much technical information as possible. I just type in biochar, epoxy, and corrosion, and I found out that there's only 219. So this is all the patents in the world. And you see that majority of the ones that are relevant are actually all filed in China now. And this one was actually one of the first ones to be reported. This is in 2021. This is actually from the author that I talked about earlier, the collaboration between researchers from Denmark and the Chinese Academy of Sciences. So they had this. So the first author on that article also filed a patent related to biocoating. But more recently, this one is from Southeast University, filed in July 2025. You see them biochar used in waterborne epoxy coatings, again for corrosion protection, improved mechanical strength, and also this one biochar in composite, and this is a powder coating, and this one is filed in January 2026 by a company, the Zhejiang Luhan New Material Technology. So you can see a lot of the advancements and innovations are now taking place in the People's Republic of China. Main strategies I'm almost finished. So main strategies for patent innovation, you normally focus on two parts. You either come up with a new composition, incorporating carbon-based additives, or you can talk about process as well. So the process will introduce a new method of synthesizing or fabricating the coatings containing carbon-based additives. And from the very preliminary patent search I did, you can say that actually you see that biochar is actually emerging as a promising carbon-based additive in organic coating systems. Actually opens up new avenues for study and investigation. Here I like to maybe explore, even for myself, functionalizing biochar in different ways to improve barrier protection properties, and also this dispersibility of the biochar, especially when you're working with nanoparticles. You want to make sure they can disperse very uniformly in the organic coating, and it has the potential to improve both the mechanical strength of waterborne coatings, also becoming very popular. As I said before, waterborne coatings becoming popular because it emits less volatile organic compounds. So actually, it's better for the welfare of the workers who apply the coatings, and And I think, if you can make them stronger than or comparable strength to existing traditional base epoxy coatings, there's a lot of value that is generated there. So I would like to conclude by saying that, carbon-based additives, they offer a sustainable path to next generation coating for the corrosion protection from our steel. Thank you. And here's my email, and you can scan this QR if you want to connect with me on LinkedIn. Thank you.